Welcome to EDU World Space.
Hi everybody. So here it's asking us, show that the case in heavy damping, and heavy damping is this. So show that a body never passes through position of equilibrium of 0 if it is A, released with no initial velocity from arbitrary position, and B, started with 0 with O with an arbitrary initial velocity. Okay, so here we're gonna have A. Okay, we have T equals 0, X equals X initial, and your velocity equals 0. So for this, we are actually looking at this equation here. So C E lambda 1, this is C1 right here, and then T plus C2E lambda 2T, okay? And then we also have this equation here, which is technically the derivative of this top one, okay? And that's the velocity. And so we're just gonna write this out because we're gonna need this to help solve our problem and for other future problems as well. So this is kind of a nice one to remember. And for acceleration is going to be a double derivative, but we don't need to worry about that right now. And so for this, we're going to go back to this and we're going to plug into the first problem the zeros. And we plug this in for, I'm going to import that as 1. So that way you guys know when I say 1 and 2, you know what I'm talking about. So we're going to plug x naught into the x. And it looks like t equals 0, and e to the 0 is 1. So we got c1 plus c2. And here you're obviously going to get, if you put c1 onto one side, you're going to get x naught minus c2. And for that, and of course, you're also going to get, if you put c2 in front, you'll get x naught minus c1 as well. So for this now, we're going to plug it in to here. So we have 0 for the x naught for the v. So we have v here for 0. And now we have c1 lambda 1 plus c2 lambda 2. Okay. And from this, what we can do is plug in here minus c2 lambda 1 plus c2 lambda 2 equals 0. And I'm just going to scroll down for you guys. Try to scroll down. There we go. I'm going to scroll all the way down. Okay. So we have that equals 0. And now what we're going to do is, just simplify it. So we have x naught minus, we got lambda 1 here, lambda 1 minus c2 plus c2 lambda 2. I'm going to have this equal to 0. X naught lambda 1 minus c2 lambda 1 minus lambda 2 equals 0. And your c2, if we solve for c2, it's going to be x naught lambda 1 divided by lambda 1 lambda 2. And similarity, if we plugged in, if I turn on my mouse here, if we plugged in for this is c2 to solve for this, you would get equals x naught minus c1. So if we plug that in into this, into our number 2 problem, we will actually get a C1 that equals x naught lambda 2 minus lambda 1, okay? It's going to be pretty much the same. And I'm just going to skip that step because it's not necessary. So now we have going to plug it all the way into our first equation. So we have x equals C1, and this is going to be our number one equation that we had above. And we have x naught lambda 2 divided by lambda 2 minus lambda 1 times e lambda 1 t plus your x naught lambda 1 divided by lambda 1 minus lambda 2 e lambda 2 t. Okay? And we can simplify this even more. And here we have x naught lambda 2 minus lambda 1. And now we have lambda 2 e lambda 1 t minus lambda 1 e lambda 2 t. Okay? And now if your t can't equal affinity and x is going to have to equal 0 for this, and so we're just going to look at this part here, and we have lambda 1 e to lambda 2 to t minus lambda 2 e lambda 1 t equals 0. And we're going to put the lambdas on one side. So lambda 2 divided by lambda 1 equals e lambda 2 minus lambda 1 t. Okay. And for this, we end up getting that your lambda is what we're kind of looking at. We're speculating. It's going to have to be between 1 and 0 for this particular problem. And also that lambda 2 minus lambda 1 is going to have to be bigger than 0. So we do find that out from the restrictions that we were given in this problem. And now we can do B. And if I remember correctly, B is asking us, started from 0 with arbitrary initial velocity. And for that, we're going to be having t equals 0, x equals 0, and v equals v naught. Okay? And I'm just going to rewrite, and let me rewrite it over here onto the right-hand side for us, okay? So we get x equals c1 e lambda 1 t plus c2 e lambda 2 t. And then we have velocity equals c1 lambda 1 e lambda 1 t plus c2 lambda 2 e lambda 2 t. And just remember, this is going to be your derivative, okay? And now we can solve, and we're just going to put the parameters like we did before into here, into these two problems. So for that, x equals 0, and so does t. So it's going to be c1 plus c2. So that means c1 is going to equal minus c2, or vice versa. And for this v1, we end up with v naught, okay, because the v equals v naught, equals c1 lambda 1 plus c2 lambda 2. And from this, we can plug in this, oops, you can do a different color. As soon as it lets me go back, there we go. We can plug this into this, okay? And if we do that, we get v naught equals negative c2h1 plus c2h2, okay? And we're going to take out C2 equals lambda 2 minus lambda 1. Okay? And because of this, we end up with a C2 equals negative V naught divided by lambda 2 minus lambda 1. And if we did C2 is going to equals C1 and we plug it in, we are going to get a C1. We're going to get a C1, and this is going to be this. There we go. And we're going to get C1 as negative V naught lambda 2 minus lambda 1. Okay. So now we're going to plug it in to our original x. So for that, we get x V naught lambda 2 minus lambda 1. And I'm just taking everything out because they both have basically the same thing. And it's just going to be E2 minus E lambda 1 t. And let's make sure that we have everything. And there we go. And because of that, we know that the lambda is going to equal 0. And your t, again, is not going to be equal to infinity. And so now we're just going to look into here. And when we do that, we get lambda 2 t minus lambda 1 t equals 0. And for this case, your damping coefficient is going to have to be bigger than the C2. And your lambda 1 is not going to equal your lambda 2. So because of this, so solution exists for t. Okay? Thank you guys.